Hi everyone. So last time we ended our discussion with crystallographic directions. So now I want to talk about how we're going to define and how we're going to kind of draw crystallographic planes now using the same Miller indice notation that we utilized previously for directions. So again, we're going to have our same Miller indice notation, coordinate system, if you will. And you'll remember last time we had this kind of notation for directions, this for families of directions, so crystallographically equivalent directions. But now we're going to use this notation for planes and similarly for family. So we could also have crystallographically equivalent planes as well, so a family of planes. So it's important to use these the correct notation when you're describing either planes, directions, or families of planes and families of directions. So with that, let's kind of draw a couple of key distinctions. So last time, it was fairly straightforward to define essentially crystallographic directions. However, planes have a little bit a kind of a unique way of defining them, but we'll see the kind of differences right now. So let me erase, and then we'll go ahead and get started. And then I'll draw my, per usual, our nice cubic cell. All right. So for planes, let's say, again, we have this notation. Let's say I wanted to draw the 1, 1, 1 plane. Now the trick here for planes is that we're going to define the intercepts. So where they intersect these HKL axes, intercepts, they are defined or given to us by the reciprocal of our plane. So the intercepts are 1 over h. That's where they're going to intersect the h-axis or our x-axis equivalently, 1 over k and 1 over l. So for 1, 1, 1, we can see that our intercepts are going to be 1, 1, and 1. So we're going to intersect here. And by intercept, we need cut through that, essentially cut through this axis or this axis or this axis, basically orthogonally. So a 90-degree angle. So it's going to cut through here, here, and here. So we just draw, connect, and there we go. That's our 1, 1, 1 plane. Nice. So now we could go and do the same essentially procedure for other kind of more unique planes. Not that the 1, 1, 1 isn't unique anyways. So let me erase again. Let's do another one. Draw my cube again. So let's do 1, 1, 0. 1, 1, 0. Let's do this plane. So same procedure, right? Intercept here, intercept here. Now here's where we run into an issue. This is infinite. So this is not something we've kind of encountered previously, but let's kind of draw our other points where we know we're going to intersect. Now, if you get an intercept like this where it's infinite, basically what it's telling you is that we're never going to kind of intercept that axis. So the L-axis or the Z-axis here, we're never going to kind of cut through it again and intercept that axis. So instead, we're parallel to it. So if I want to cut through the H and K axis and never hit my Z, I'm just going to go and drop like this. And here it is. That's my 1, 1, 0 plane. So again, another little, kind of trick. So remember, if you see this 0, or if you have this intercept here, or it's infinite, remember, parallel to this plane. It's never going to kind of cut through and intersect the axis that way. So it's just going to continue along parallel forever. Excellent. Excellent. So let's do another one that's a little bit trickier. Or actually, let's do a kind of an inverse problem right now. So I'm going to actually draw a plane, and then I'm going to have you describe it for me. So I'm going to, oh, sorry, I still have my eraser on. Switch. Let me draw a little bit. So just for everyone, this is basically a half where it's intersecting here. So what's happening on this one? How am I going to kind of, I want to figure out now, how do I describe, what is this plane? Well, I know that it's going to intercept 1, my h at 1, right? So my intercept is equal to 1 over 1. Does it ever intercept my k-axis? No, it's parallel to it. So this is going to be 1 over 0, infinite. Now what about L? L is going to be 1 over intercepts here at a half. So this plane will be 1, 0, and 2. Excellent. Everyone see that? So you just flip that intercept. Nice. And we'll do one more example of a particularly actually tricky one. So we'll see if you can guess and figure this one out. It's our last kind of little trick when you're dealing with crystallographic planes. So let me draw this real quick. Kind of similar to the last one. But nicer. And right there. So does anyone see the kind of issue right off the bat with this one? Well, at our kind of usual origin, we see that our plane is actually intersecting all axes. So every axis is being intercepted at 0, which is kind of nonsensical, and you can't, write essentially a plane like that. So the trick here is going to be we have to redefine our origin. So I'm going to redefine my origin. Make it red, it's a bit clearer. I'm going to redefine my origin here at O prime. So let's figure out, just like we did last time, and figure out our intercepts. So in this new origin, do we ever intersect H? Which we'll kind of draw it out a little bit right here. So remember, our new H is this way. No, we're never cutting through H. But, so let's draw that right now. 1 over 0. But we are cutting through K at the intercept is -1. And L, same thing here. I'm trying to show a half. Same procedure as last time. So our plane is 1, O, -1, the hat, and 2. Perfect. So remember, if you have a plane that cuts through essentially your typical original origin, all you have to do is redefine your origin and then proceed as usual. Find those intercepts, take the inverse, and you have your planes. Nice. So just as there were families of crystallographic equivalent planes, there are also, or directions, there are also families of crystallographically planes as well. So let's look at an example. So let's look at, erase here. Let's look at the 100 plane. So the 100 plane is just going to be that front face right here, 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 here. And now remember, same exercise last time. So if I rotated around our k-axis, you couldn't tell the difference between this plane and this one. Right? If I blindfolded you, again, same rules. So same, instead of the magnitude this time, same area. And if we have a simple cubic cell we're passing through, we have the same, basically, planar density of atoms. We'll come back to that in a second. So we would define, again, just as usual, 100. And this would include the same, you can imagine this same is crystallographic equivalent, so is this one, so is this one, all the faces essentially. And you could have families that are 110, just like last time. So that's crystallographically equivalent planes. Those are how do you draw crystallographic planes and how do we identify the trick here. So remember, you don't multiply out by the least common kind of multiple and get it into integer values. It's just kind of the inverse of these intercepts here. So find the intercepts, take the inverse, that'll give you your planes. If you have a plane, find the inverse and get the intercepts and draw it. So we'll talk next time, and actually we'll start to calculate something that I've hinted at in this video, which is planar density of atoms, which is going to be very important for kind of mechanical properties and slip and how dislocations move about. So I'll see you next time. Thanks.